Hello, welcome. In this part of the lecture, we will discuss some spatial sequences and compute their limits. Theorem. If P is a positive real number, then the limit of 1 over n to the p as n approaches infinity equals to 0. If p is a positive real number, then the limit of the nth root of p as n approaches infinity equals to 1. The limit of the nth root of n as n approaches infinity equals to 1. If p is a real number strictly greater than 1 and alpha is any real number, then the limit of n to the alpha over p to the n as n approaches infinity equals to 0. If the absolute value of p is smaller than 1, then the limit of p to the n as n approaches infinity equals to 0. For all real number p, the limit of p to the n over n factorial as n approaches infinity equals to 0. The last limit shows that the factorial function increases much faster than any power function. So the factorial function dominates over the power function. Let's try to prove some of the statements. Let's define x sub n equals to the nth root of p minus 1. It is sufficient to prove that the limit of x sub n as n approaches infinity equals to 0. Then, by the proposition 7.1.1, namely, so this proposition says the limit of a sub n as n approaches infinity equals to a if and only if the limit of this new sequence a sub n minus a as n approaches infinity equals to 0. It simply allows us to move the limit from the left-hand side to the right-hand side, or from the right-hand side to the left-hand side. Now, to show that the limit of x sub n as n approaches infinity equals to 0, we first consider that the real number p is greater than 1. So in the hypothesis, it was given as a positive real number. So in the first case, we are considering p is greater than 1. Thus, by the Bernoulli inequality, we have p equals the nth power of 1 plus x to the n, which is larger than or equal to. Here we applied the Bernoulli inequality. The first equality came from taking the nth power of the quantity. Here. So now the equation here can be written in this form by solving for x sub n. And we earlier proved that x sub n is positive. We have these two inequalities. Since the limit of p minus 1 over n equals to p minus 1 times the limit of 1 over n, which is equals to 0, by the squeeze theorem, the limit of x sub n must also be 0. So this concludes the proof for the case if p is greater than 1. Similarly, if p is positive but smaller than 1, then 1 over p must be greater than 1. From the first part, we have the limit of the nth root of 1 over p, which is greater than 1, equals to 1. Therefore, the limit of the nth root of p as n approaches infinity can be written to be equal to the limit of 1 over the nth root of 1 over p. And then by the quotient rule of limit, we can write this is equals to the limit of 1 over the limit of the quantity nth root of 1 over p, which gives 1 over 1, simplifies to 1. Now, it is left to prove that the statement is true for the case p equals 1, and which is obvious. Because the nth root of 1 is always 1, this becomes a constant sequence. So this completes the proof of the statement A. Now let's try to prove the statement D. Namely, if p is a real number greater than 1 and alpha is any real number, then the limit of n to the alpha over p to the n as n approaches infinity equals to 0. Take a positive integer k greater than alpha. Such a positive integer exists by the Archimedean property. Since p is greater than 1, let p equals to q plus 1 for some q positive. Then we choose an integer n, which is greater than 2k. The reason will be made clear later in the proof. Now, by the binomial theorem, we have the nth power of p, which is equal to the nth power of 1 plus q, which is greater than n choose k times q to the k. With the n choose k, the expression is in fact n times n minus 1 times up to the factor n minus k plus 1 over k factorial. And we have the q to the k. Now for the chosen n greater than 2k, we have n minus k plus 1 is strictly larger than n over 2. Therefore, each factor in the numerator here, for example, n is greater than n over 2, and n minus 1 is also greater than n over 2, and all the way up to the factor n minus k plus 1 is greater than n over 2. So the product of the left-hand sides is greater than the product of the terms in the right-hand side, namely n minus 2. And we have k many such factors. So it would be n over 2 to the k. So we have n to the k over 2 to the k. And we also have k factorial here and q to the k here. Please pause the video and confirm the inequality. Therefore, p to the n is greater than this quantity here. So the 1 over p to the n is strictly smaller than the quantity here, which is the inverse of the right-hand side. Now, by multiplying by n to the alpha by both sides, we obtain this inequality. We multiplied both sides of this previous inequality by n to the alpha. And the term here can be rewritten in this form, where the first factor is constant, meaning independent of n, and the second factor, 1 over n to the k minus alpha, approaches 0, since 1 over n to the p approaches 0 by part A if p is positive. So, by the squeeze theorem, now the result follows. The sequence approaches 0 for all real number alpha and for all real number p greater than 1. Please pause the video now and try to confirm the inequalities. Let's try to prove the statement E, namely, if the absolute value of p is smaller than 1, then the limit of p to the n as n approaches infinity equals to 0. Since the absolute value of p is smaller than 1, so the 1 over absolute value of p is greater than 1. So we define 1 over absolute value of p equals to 1 plus h for some positive h. Then 1 over absolute value of p to the n equals to 1 plus h to the n, which is, by Bernoulli inequality, can be written as greater than or equal to the quantity 1 plus nh. Therefore, if we invert this inequality, we obtain the absolute value of p to the n is smaller than or equal to 1 over 1 plus nh, which is smaller than or equal to 1 over nh. Now, since this sequence approaches 0, and the sequence, the modulus of p, or the absolute value of p to the n, is larger than 0, so this is the constant sequence, which is also approaching 0, so another result follows from the squeeze theorem. This concludes the proof of the statement E.